Hello. My name is Ann, and today I'm going to be talking about bipartite graphs. And lucky for you, today's going to be a nice short one, and that's because we don't explore a more complex application of bipartite graphs until we get to assignment problems, aka allocation problems in Unit 4. So yeah, let's get straight to it. As usual, the place that we're going to begin is to define a bipartite graph. Now, a bipartite graph is actually a special subset of simple graphs. And in case you don't remember what a simple graph is, that's just a graph that doesn't have any multiple edges or loops. And if you still don't know what I'm talking about, please go back to my Introduction to Graph Theory video, where I have most of the basic graph theory terminology beautifully timestamped for your reference. Anyway, the special feature that sets a bipartite graph apart from the rest of the simple graphs is that all of the vertices can be divided into two distinct groups or sets. On the screen here, you can see an example of a bipartite graph, where the first group of vertices are labelled A, B, and C, and the second group of vertices are labelled 1, 2, 3, and 4. Now, you can't just randomly divide these vertices into two groups. There are conditions that need to be followed. So the vertices within each set are not adjacent. What that means is that a vertex in one group is never going to be directly connected to another vertex in the same group. Another way to look at that is that the edges in a bipartite graph always begin at a vertex in one group and end at a vertex in the opposing group. Okay, so this first example asks us to determine whether the following graphs are bipartite. Now, to do this question, you will need two different coloured pens, pencils, highlighters, texters, whatever you've got on hand. Lucky for me, this is an all-in-one. Anyway, I'm going to start with part A, and I'm going to colour in any vertex in my first colour. So I'm going to choose to colour in this one here. Now, my next step is to look for any vertices that are adjacent to this and colour that in the second colour. So I'm going to colour in this vertex in green. Next, I'm going to repeat the process. So any vertices that are adjacent to this green one now need to be coloured in orange. So I've got this vertex here, and the one that I initially coloured in already. Next, I'm going to switch back to green, look for any vertices that are adjacent to these new orange ones and colour those in the opposite colour. So that's going to be green and that is going to be green. Now, because I was able to colour in all of the vertices without any of them clashing, aka being adjacent within the one group, I can tell that this graph is bipartite. And moving on to part B now, where I'm going to do exactly the same thing. So I'm going to choose any starting vertex and I'm going to colour that in my first colour. Next, I'm going to look for any adjacent vertices and colour those in my second colour. So in this case, that'll be this vertex and this vertex, which are adjacent to that first green one. Repeating the step again, any vertices that are adjacent to these two new orange ones now need to be coloured in green. So I've got this one, and I have encountered a problem because I need to colour this vertex in green because it's adjacent to this one, but by colouring that one in green, I'm going to be creating adjacent vertices in the same colour. So I'll just show you there, right? So these two vertices are adjacent and these two vertices are adjacent because they're all the same colour, aka in one group. That is not allowed in bipartite graphs. That means that this graph is not bipartite because I can't separate the vertices into two groups where the vertices aren't adjacent within the groups. So this is not bipartite. So this next example is a really simple one, but the main thing that I want you to take away from this is recognizing the types of practical situations that bipartite graphs can be applied to. So anything where vertices can be split into two groups, keep that in mind. Let's read the question. The possible allocation of jobs on a construction site are summarized below. Amir can complete all 5 tasks, Bella can complete tasks 2 and 4, Chris is on vacation leave, Darren can complete tasks 3 and 5. So when I read those dot points, I can see that I will be able to use 2 groups of vertices, where the first group are going to be the workers, Amir, Bella, Chris and Darren, and then the second group will be the tasks. There are 5 tasks, so they're going to be labeled 1, 2, 3, 4 and 5. And that's what the question asks us to do, construct a graph to display this information. So I'm going to use 4 vertices to represent the 4 workers, and then 5 vertices to represent the 5 tasks. Now I do need to label each of these vertices. So I've got Amir, Bella, Chris, and Darren, who are my workers. So I can go one step further and label the set of vertices like that. And then I've got task 1, 2, 3, 4, and 5, and I can label those as tasks as well. Now I need to add my edges in. So starting from the first dot point, Amir can complete all 5 tasks. That means that I'm going to connect Amir to every single vertex in my second group. Bella can complete task 2 and 4. So I'm only going to connect her to task 2 and task 4. Chris is on vacation leave, so we're not going to connect him to any tasks. He can't do anything. Darren can complete task 3 and 5. And there we have it, a completed bipartite graph to display the information. And that is all I have for you guys today. I told you it was going to be a short one. If you found the video helpful, please give it a like. And if you don't mind seeing a bit more of me around, consider subscribing to really support the growth of my channel. Anyway, I'll see you next time. Bye.